We just finished with the introduction and the historical part, mostly about Bitcoin, and we are finally getting into, we are getting into the Ethereum meat of the white paper. So let's start. Ethereum. The intent of Ethereum is to merge together and improve upon the concepts of scripting, altcoin, and on-chain meta protocols, and allow developers to create arbitrary consensus-based applications that have the scalability, standardization, feature completeness, ease of development, and interoperability offered by these different paradigms all at the same time. Okay. Ethereum does this by building what is essentially the ultimate abstract foundational layer, a blockchain with a built-in Turing-complete programming language, allowing anyone to write smart contracts and decentralized applications where they can create their own arbitrary rules for ownership, transaction formats, and state transition functions. Okay, so I think the crux here is that, contrary to Bitcoin, which was the main application was the tracking of transfer of currency, Bitcoin currency, Ethereum wants to make a computer. So they would keep the consensus aspect, which is the one which orders transactions, but instead of having transactions only changing the state of UTXOs of account, they will use transactions to change the state of a virtual machine, and they will extend the scripting language to include everything that makes it Turing complete. So loops are missing, and okay, so a couple of things are mainly missing: loop and memory storage. So Bitcoin does not have memory storage, right? You can only store UTXOs, but that's implicitly done by the system. Your script cannot decide to allocate memory. Okay, a bare-bone version of Namecoin can be written in 2 lines of code. Wow, that's pretty impressive. And other protocols like currencies and reputation systems can be built in under 20. Okay, smart contracts, cryptographic boxes that contain value and only unlock it if certain conditions are met, can also be built on top of our platform with vastly more power than that offered by Bitcoin scripting, because of the added powers of Turing completeness, value awareness, blockchain awareness, and state. Right, so these are the 4 things that they mentioned earlier. So as a quick recap, Turing completeness was the fact that the scripting language didn't have loops and memory. So there was not a Turing machine. Value awareness was that you could create so UTXOs could not be broken apart, so your contract could not know the value of the UTXO. You would just either allow the UTXO to be spent or not spent, but it could not essentially create new transactions or create new UTXOs. Blockchain awareness was the fact that the script would not have access to any metadata about where the transaction was, so it would not know which block it was part of. It would not know then the block hash, the block height, and so on and so forth. And finally, state was that in Bitcoin, the scripts do not have access to the current state of the blockchain. So you could not know if, for example, another UTXO was spent or not. Ethereum accounts. In Ethereum, the state is made up of objects called accounts, with each account having a 20-byte address and state transitions being direct transfer of value and information between accounts. So that's already new. In Bitcoin, you did not have accounts. You only had UTXOs. And the idea of an account, like what we call an address in Bitcoin, was an abstraction based on top of UTXOs. So what we were saying is that if the UTXO, so we know that UTXO has a script attached to it, which is the script between quotes the challenge that the spender had to fulfill, usually by providing a signature. But the script didn't have to be that particular challenge, and over time, different kinds of templates, or we say, or standard scripts emerged. The first one was actually not the one that we currently use now. The first one was really includes the public key, so the full public key, which was 256 bits, and then asking the spender to sign the message for that public key. But this script was actually fairly long because public key is 32 byte. Then soon afterwards, the challenge was only providing the hash, the MD ripe MD20 of the public key. So only a 20 byte address, so similar to what Ethereum has now. And the challenge was to provide both the public key and the signature, and the script would check that the public key provided would hash to the value that is inside the UTXO. So by extension, that particular script, the one that contains only the hash of the public key, became the new standard, and converting this 20 byte address into a more readable form became the address. So Ethereum takes account into first class citizen. So now accounts is part of the model. Ethereum account contains 4 fields. The nonce, a counter used to make sure each transaction can only be processed once. So this is also something that Bitcoin doesn't have, of course. The account current ether balance, the account contract code if present, and the account storage. All right. So this is already like way different, because now we are saying that the address. So address now becomes the particular key element of the Ethereum state, the blockchain state. So before in Bitcoin, the state was UTXO. Now he's saying that the root of the tree, the state tree, is the account. And then under account, you would have a balance. So that's pretty standard. But now you also have this contract code. So that's going to be programs, basically. And there should be then, so he says that if present, so it seems like contract code is optional. So it seems to say that you can have 2 kinds of addresses of accounts, one that have contract and one that does not have a contract. So the one that does not have a contract would be very similar to a wallet address, because it only has ether balance. But the only thing that it has more is this nonce, right? So the nonce makes sure that since it's stored in the blockchain, so implicitly stored in the blockchain, or maybe explicitly, I don't know actually. We'll see it later. You will not be able to send a transaction that repeats the same nonce. So it's a counter that makes sure that when you send a transaction, you will send a transaction to a particular account with a nonce, and then they will probably hash that to get a unique key. Ether is the main internal crypto fuel of Ethereum and is used to pay transaction fees. In general, there are 2 types of, wow, this is pretty cool. External owned accounts, so that's what I was going to, I just said earlier. So the ones that controlled by private keys, and contract accounts controlled by their contract code. So if you have an account or an address that does not have contract code, that will be an externally owned account. and the way for you to send transactions from that address is to have the private key. And then you have contract accounts controlled by the contract code. So that's going to be interesting to see how it works. So these contract accounts, you're not going to be able to transact directly from them because they would not have a private key. An externally owned account has no code, and one can send messages from an externally owned account by creating and signing a transaction. So this is standard Bitcoin stuff, right? In the contract account, every time the contract account receives a message, its code activates, allowing it to read and write internal storage and send other message or contract in turn, and create contract in turn. So the contract account is like a mini program, and when it receives a transaction, you are basically going to call a function or a method in that contract, and you're going to execute some code, and that code is capable of changing its internal storage. So now each contract account is like a mini computer basically, and it will be able to then either call other contracts or even create new contracts. So this whole thing is completely new, right, compared to Bitcoin. Messages and transactions. Messages in Ethereum are somewhat similar to transactions in Bitcoin, but with three important differences. First, an Ethereum message can be created. Let me see if I'm still recording. Yeah. First, an Ethereum message can be created either by an external entity or contract, whereas a Bitcoin transaction can only be created externally. Okay, so that's what we say about transactions. A script cannot create a transaction in Bitcoin, but in Ethereum, message can be created by external entity by making a transaction basically to the blockchain, to the network, and having it mined and put into a blockchain, and also by contract in turn when they execute code. Second, there's explicit option for Ethereum message to contain data. Okay, so message in Ethereum also have this payload. So it's really more likely like a function call. Whereas in Bitcoin, the only thing that you have is UTXO, so there was no data associated. Finally, the recipient of an Ethereum message, if it's a contract account, has the option to return a response. This means that Ethereum message also encompasses the concept of functions. Yeah, basically what we said. The term transaction is used in Ethereum to refer to the signed data package that stores a message to be sent from an externally owned account. Transactions contain the recipient of the message, a signature identifying the sender, the amount of either and the data to send, as well as two values called start gas and gas price. Okay, so that's the distinction they're making, is that the message is basically the logical part that you want to send, right? So it will have it has a destination, it has parameters, so the data. But transaction is the end, also has the envelope. So the envelope will have the signature. So the signature makes sure that the message sender is correct. So it's make sure that you're not impersonating another account. So that's the amount of ether and there to send. So that's actually the payload, the content of the envelope. And then you have these two things, the start gas and the gas price. So they will explain what it means, right? In order to prevent exponential blow-up and infinite loops of code, each transaction is required to set a limit to how many computational steps of code execution it can spawn, including both the initial message and any additional messages that get spawned during execution. Okay. All right. So the thing is, like, since we cannot determine a priori how much computational resources code will require. So by looking at a piece of code in a Turing complete language, you cannot know how long it would take, or not only in terms of time, but also in terms of execution steps. So especially if it has a loop, you don't know if the loop is not going to be infinite. So the idea here is that when you make the call to a function, you also set the cap to how much gas it's going to use. So it seems to imply that every code execution step, so every instruction that this code will run, will have a gas usage, amount that he will spend, and then the virtual machine will start executing the program, and then accumulate the gas usage that it has to use, it has to spend. And if you hit the gas limit, then this transaction will not pass, will revert. Right? If transaction execution runs out of gas, all state changes revert. So if you are running out of your usage of your allocated limit, then boom, the transaction is cancelled. But you still pay the fees, right? And if transaction execution halts with some gas remaining, then the remaining portion of gas fees return to the sender. So you set the gas limit, which is how much you're willing to pay, but you're not going to pay necessarily that amount. If you're using less than that amount, the remaining is returned to you. There is also a separate transaction type and corresponding message type for creating a contract. The address of a contract is calculated based on the hash of the account nonce and the transactional data. Right. So this is interesting. So this tells you how the contracts are created. If you if you make this special transaction, they will get the account nonce and then the content of the contract. So this ensures that the contract address is going to be unique, because even if you submit exactly the same contract data, so the same contract definition, exactly the same contract code, since the account nonce is guaranteed to change, then the resulting hash will be different. Therefore, the contract address will be different. An important consequence of the message mechanism is the first-class citizen property of Ethereum. The idea that contracts have equivalent powers to external accounts, including the ability to send message and create other contracts. Okay, so since the external account can create contract, but the contract can also create contracts, they are equivalent in terms of what they can do. This allows contracts to simultaneously serve many different roles. For example, one might have a member of a decentralized organization, a contract, be an escrow account, another contract, between a paranoid individual employing custom quantum proof Lamport signature, a third contract, and a co-signing entity which itself uses an account with 5 keys for security. So what it mentions here is that you can have a bunch of contracts, each having different rules, and each using different signatures. Right? One is using a 5 key for security, one is using a quantum proof Lamport signature, and then finally an escrow contract. So it means that they are implying that you can extend the security of your accounts by requiring different kind of signatures if you implement these signatures as smart contracts. Right. The strength of the Ethereum platform is that the decentralized organization and the escrow contract do not need to care about what kind of account each party to the contract is. Right. So you have different layers here. You have the escrow account. Right. So escrow account is just gonna be in charge of locking a certain amount of ether and unlocking it if they receive the proper call from known addresses. And they don't care about how the call is being made. So if it's made by a normal entity by an external account, it means that somebody will have to sign a transaction and send that to that escrow account. But it doesn't have to be that way. It could come from another contract, and that contract could require even more advanced security than the normal Ethereum signature. Okay. So he's saying that it can come from an account that is containing a smart contract using a custom quantum proof lamport signature. And the smart contract escrow contract doesn't care about where it is coming from, right? So you can make that contract independent from the other contract, and that's a very good property in the sense that it makes the escrow contract independent from the whoever wants to participate. Okay, so we have drawing here. The Ethereum state transition function. Okay, so this is going to be similar to the Bitcoin one. It's defined as follows. Check if the transaction is well formed. Okay, so the signature is valid and nonce match is a nonce sender account. This is the same as, this is similar to what Bitcoin has, except that now we have the nonce, right? Calculate the transaction fees as start gas plus gas price. We didn't say what gas price was, but by this formula, he said here, and gas price is the fee to pay to the miner per computation step. So this is actually interesting too, because the gas price is not fixed, right? So if you want to incentivize the miner to get to process your transaction, even though it has a low gas usage, you can arbitrarily set the gas price, right? So you can set a high gas price and the miner will get a higher fee. So calculate the transaction fee as this product and determine the sending address from the signature. Subtract the fee from the sender account balance and increment the sender nonce, right? If there's not enough balance to spend, boom, return an error. Okay, so it implies here that the fee is deducted. I'm not sure about this actually. I don't know what happens if you don't have enough fee. Will you get? I think that if you don't have enough fee, it will revert and leave the whatever balance you have. Right. So if the fee is very high, greater than your account balance, it will revert, but you will still keep the account balance. But let's see if that's clarified. Initialize gas equals start gas and take off a certain amount of gas per byte to pay for the bytes in the transaction. So the transaction itself has a price in gas. Okay, so that's independent from the execution. Transfer the transaction value from the sender account to the receiver account. If the receiving account does not get exist created, if the receiving account is a contract, run the contract code either to completion or until the execution runs out of gas. Okay. So you pay if the value transfer failed because the sender did not have enough money, or the code execution ran out of gas, revert all state changes except for the payment of fees and add the fees to the miner's account. Okay, so I think this refers to up to 3 then. So I would say that you will pay the fees for the execution and the transaction fees, but not for this part. Okay. So I think it pre-allocates the fees. Okay, let's see if it's clearer afterwards. I think that's what it means. Yeah, it's, let me think. Start gas. I thought start gas was the limit. Okay, okay, I see what it means. So start gas is actually the limit. So first you check if the account has enough. So you multiply that by gas price, and this is essentially what the account is willing to pay as a maximum. And you check that you have at least that amount of money inside the account before doing it. Then you start the transaction in the EVM. So you execute the contract if it's a contract code. And if you run out of gas, so if your actually expenditure reaches start gas or exceeds start gas, you revert the changes, but the account will have paid that amount. So this is non-refundable. And if it was less, then you will refund the difference, right? Otherwise, return the fees for all remaining gas to the sender and send the fees paid for gas consumed to the miner. So you basically want to set this guy right, because if you set it too low, then you will hit that limit. You will spend that gas, but your code will not be executed. So you have wasted that gas. If you set it too high, then you are willing to pay that much. So first of all, you need to have that much in your account, and you may actually spend more than you really intended. So because if it doesn't hit that limit, then the transaction will go through. So you really should make it sure that this is what the maximum that you want to pay, and not regret it later if you actually your transaction hits like start gas minus 0.10001 ether. So really get close to that, but not exceed that, because the transaction will go through and your account will be debited. For example, suppose that the contract code is if not contract storage message data 0, contract storage message data 0 equal 1, right? Note that in reality the contract code is written in the low-level EVM code. So EVM stands for Ethereum Virtual Machine, right? This example is written in Serpent, our high-level language for clarity, and can be compiled down to EVM code. Suppose, I thought it was Solidity. Okay, well, suppose that the contract storage starts off empty, and the transaction is sent with 10 ether, 2000 gas, 0.001 is the gas price, and $2 field, 2 Charlie. Alright, so when you send the transaction, you basically also send parameters, right? So that would be message data 0 would be 2, and message data 1 would be Charlie. The process for the state transition function in this case is as follows: check the transaction is valid. This is probably going to be true. Check the transaction sender has at least 2000 times 0.001, so that's 2 ether. So you're willing to spend 2000 gas for a price of 1 milli ether per gas. So that means that you're willing to spend 2 ether in total. If it is, then subtract 2 ether from the sender account. Initialize gas 2000. Assuming the transaction is 170 byte long and the byte fee is 5. So that's 170 times 5. Subtract 850. So that's 850, right? So now you have 1150 gas left, 1150 gas left. Subtract 10 more ether from the sender account and add it to the contract account. Yeah, because you're spending 10 ether, right? Yeah, run the code. So in this case, this is simple. It checks that the contract storage at index 2 is used. Notice that it's not, and so it set the storage at index 2 to be the Charlie. So this is just basically saying if you don't have the slot used, create it and set it to Charlie. Suppose this takes 187 gas, so the remaining is 963, and then you return 963 milliliter back to the sender. That's it. If there was no contract at the receiving end of the transaction, then the total transaction fee will simply be equal to the provided gas price multiplied by the length of the transaction byte, and the data sent along the sender will be irrelevant, right? So if you're sending to this transaction to an address that doesn't have a contract, so you made a mistake, or you send it to a non-existing address, or you send it to a regular external account, then the second part, this 5.6 will not apply, right? And but you will still send this 10 Ether to that address, and you will still spend that part here. Additionally, note that contract initiated messages can assign a gas limit to the computation that they spawn. Okay, so when the message comes from a contract, it can also set the gas limit. So when you send a message from your own account, you set a gas limit, which is the start gas, and the contract initiated message can do the same. And if a sub-computation runs out of gas, it gets reverted only to the point of the message call. Right? So this part here is interesting, because it says that since contracts are first citizen, they also can initiate messages with the same parameters, with start gas, blah blah. But in their case, if they run out of gas, the entire thing will not revert. It would only revert from the point that the call was being made, the message was being sent. Okay. Hence, just like transactions, contracts can secure their limited computation resources by setting strict limit on the sub-computations they spawn. So just terminology, sub-computation is basically a call that is made from a contract to another contract. Code execution. You see there's a good stopping point. Okay, I think we can do this section and then we can stop. Code execution. The code in Ethereum contracts is written in a low-level stack-based bytecode language referred to as Ethereum Virtual Machine Code, EVM. Yeah. The code consists of a series of bytes, where each byte represents an operation. Okay. In general, code execution is an infinite loop that consists of repeatedly carrying out the operation at the current program counter, which begins at 0, and then incrementing the program counter by 1 until the end of the code is reached, or an error or stop or return instruction is detected. The operations have access to 3 types of space in which to store the data. Okay, so the first part is pretty standard. The stack-based thing is most of the virtual machines are stack-based. So stack-based refer to the intermediary state that the code has to carry out calculations. And using a stack is very common these days, because it's pretty easy to implement, and the model is not limited to a certain number of slots. The earlier virtual machine would use registers and say that basically you have a certain number of variables, of slots, and then you have all your opcodes will operate on these registers or slots. So that's actually what the most CPUs are using. But when we're talking about a virtual machine, it's more flexible to say that you have a stack. So stack would be so if you're used to Hewlett-Packard calculators, you're used to this notion of a stack for operations, and if you're not, you can of course take a look at Hewlett-Packard calculators. I think it's beyond the scope of here to explain how stack works. But what we're saying here is that normally they will execute instruction after instruction, and each instruction will potentially change the stack. And then if either you reach the end or you reach an error, but you can also return at the in the middle. So return if you if you return some value, and stop is if you want to abort and not return any value. And error if the virtual machine detects that something should not have happened. Like for example, you are spending more money than you're supposed to, and then or your signature doesn't match, and it raises an error. So I guess error are more like exceptions. Stop is when your program wants to abort, and return is when your program wants to return from the middle. Otherwise, it will reach the end and then basically stop or return at the end. The memory that you can use in your program is the stack, of course, right? But the stack is a last in first out container to which 32-byte values can be pushed and popped. So the stack will be used while the program is executing, but at the end of the execution, the stack is gone. So if you want to store anything beyond the execution of your contract, then you cannot use the stack. So you also have a memory, infinitely expandable byte array. So this memory is also transient, because the next one it says is long-term storage. So I'm gonna guess that memory is also gonna be wiped out after the execution finishes. But contrary to the stack, this memory is not organized as a last in first out container. So it's more like a heap in traditional programming languages. So this stack and memory, if you're programming, is very standard way to have storage. So the last one is the new guy. So this is like the heap, and this is like the stack. This contracts long-term storage, a key value store where keys and values are stored are both 32 bytes. Unlike stack and memory, which resets after computation ends, storage persists for the long term. So that guy here is kind of like your database. Right? So while this memory will be deleted once the contract execution ends, this is your disk storage, but it has to be organized as key value store. So I'm gonna which logically this should be the cheapest, and this should be a bit more expensive, and it should be like really expensive, because each node will have to keep that storage permanently while you allocate it. The code can also access the values, sender and data of the incoming message, as well as block header data, and the code can also return a byte array of data as output. So that's the improvement on Bitcoin. The transaction or the contract code can use the blockchain data, block header data. I don't know if you can use past block header data, but at least you can use the current block header data. And the code can also return data, so that was also not possible with Bitcoin. The formal execution model of EVM code is surprisingly simple. While the Ethereum virtual machine is running, its full computational state can be defined by the tuple, block state, transaction, message, code, memory, stack, program counter, and gas. Not sure why they call it very simple. I wouldn't say it's so simple, but so block state, well, it's this guy here, right? Plus everything else that you have there. And transaction, of course, you have access to your transaction, message, code, memory. So that part is relatively normal. And it says that you also have memory and stack. Okay. I thought we also get storage. I don't know why I didn't get storage. I guess storage is part of memory. It's a bit weird. Program counter. So this determines where you're at in execution. And gas is how much you have left of gas. Where the block state is the global state containing all accounts and includes balances and storage. Oh, there you go. I should read more. So block state contains the storage. That's why they don't mention storage here. Every round of execution, the current instruction is found by taking the PC's byte of code, and each instruction has its own definition in terms of how it affects the tuple. Right? For example, add pops 2 items off the stack and pushes their sum, reduces gas by 1, and increment the PC by 1. And SS store, storage store, pushes the top 2 items off the stack. Okay, I will say pops then the top two items off the stack, and insert the second item into the contract storage at the index specified by the first item, as well as reducing gas by up to 200 and incrementing PC by 1. So this stuff over there that we were saying, this stuff here will probably turn into a S store, and passing these two guys to Charlie. So when the EVM executes store with these two arguments, it will create storage slot 2 and put Charlie there, and that costs up to 200. Not sure why it's up to 200, but I don't think it's very important. I would have guessed that it would be a fixed price, but maybe it depends on something. Maybe it depends on what the length of what you store. Probably not, because I think it must have a limit as well on the length of what you store. Anyways, and that is no, we're not here. Although there are many ways to optimize Ethereum via just-in-time compilation, a basic implementation of Ethereum can be done in a few hundred lines of code. Well, I think that really highly depends on the complexity of the EVM language. So a few hundreds may be very optimistic in my opinion. But I mean, let's take their word for it. But because it depends on the how many opcodes you have. But I think their point is that it's not super complicated in the sense that you only have a stack is very easy to implement in code. So there are data structures that are really like a stack already. Memory is a byte array, so it's also fairly easy to use to implement. You use a byte array, and byte arrays already are expandable in most programming languages. And that contract long-term storage could be done with a database or a hash map, a key value store. So these data structures are fairly easy to implement. And now the logic of the EVM is basically looping through your code, keeping track of the PC, reading the opcode at that particular location, and then running that opcode. So there will be basically a loop that reads that instruction, and then a massive switch on which instruction it is. And for each type of instruction, you would get the parameters, and then just basically execute it. And the result will be either increment that you use gas. So each instruction would have a gas cost that you deduct, and then you increment the counter by 1. Also suppose that some of these instructions will be loops and will let you jump back to a previous location. Otherwise, we are back to having a non-Turing complete language, non-Turing complete machine. Okay, so that is it for EVM. So I'm gonna stop here. If you have any comments, please add them. And otherwise, we will continue with blockchain and mining in the next section.